Viewers, sure you are doing great. It's nice to meet you once again as we enjoy the ride of physics. Yeah, the other time we talked about the fundamental quantities and the derived quantities. Now we discussed about the dimensions. Now at this point we are moving towards the scalar quantities and the vector quantities. We need to understand this concept. First of all, what is scalar quantities? Scalar quantities are those quantities that has magnitude but no direction. Example, speed. Now, example, distance. Yeah, speed, distance. But we want to talk about vector quantities. Vector quantities are those quantities that has magnitude as well as what? Direction. Example is displacement. Example is velocity. Now, let's distinguish briefly between scalar quantity and the vector quantity. The scalar quantity has direction. The scalar quantity has no direction. The vector quantity has direction. The scalar quantity only has magnitude. The vector quantity has the magnitude as well. Now, let's take for instance speed and velocity. Speed is distance over time. Velocity is displacement over time. You need to understand that the difference between speed and velocity is that speed is just distance all over time. So that means time is equal to scalar quantity because it's just a magnitude and extent, but there is no direction to it. But out of the velocity is what? Displacement over what? Over time. So now when we talk about displacement is the change in the position of something with respect to a direction. Change in the position of something with respect to a specific direction. So speed is distance over time, is distance over time without a direction. Distance is scalar, speed is scalar. Displacement is vector because it has a direction. So, but both of them have the same unit. Speed is what? Meter. Distance is meter. Then time is seconds. While the vector quantity as well is also displacement is also a meter per seconds. So you need to know. We can say speed is the distance moved by an object in a specified direction, while velocity is the distance moved by an object in a specified direction. So just briefly note that. Now the question comes to us this in each of the quantities in the following indicate the scalar or vector at the front, V or X. That is, V stands for vector and X stands for scalar. Now, an example is 1, pressure. Is pressure a scalar or vector class? Of course, pressure is a scalar quantity. Yeah. Although it's force, the ratio of force to area, but then there is no direction to what it is tending towards. Pressure can occur at any point, can occur also. Is a scalar quantity. Electric potential is a scalar quantity. Let me indicate it with X. Electric potential, it is a scalar quantity X. Impulse is actually the product of the force of an object with time, product of force and time together. So the force is actually the product of the mass and acceleration, and the acceleration is a function of the velocity with time, and velocity is the displacement with time, and displacement is distance in the direction. So that means direction is involved in that impulse. When you exert a force or something with respect to time, that force is acting as a direction. So it's a vector quantity V. Impulse is a vector quantity. Specific heat capacity. Specific heat capacity is actually the quantity of heat needed to change a unit mass of a kilogram in 1 degree Celsius. So just a mass is talking about an object, it's not talking about direction. So it's a scalar quantity X. Now altitude is actually height. So that is just distance in a vertical direction. So but it is vertical, but there is no direction. Altitude just ordinary height. So it's a vector, is a scalar quantity. Momentum is the product of the mass and velocity of an object. Mass, velocity itself alone is a displacement with time, so it has direction. So momentum is actually a function of an object acting at a specific direction. So is a vector quantity. Electric potential difference. Yeah, electric potential difference. We can say potential is actually the movement of a coulomb done by an object. The work done in moving a coulomb of charge from one point to another in an electric circuit is reversed as the potential difference, the electric potential difference. So work done moving a column of charge from one point to another, one point. So it's a vector, is moving from one place to another. It's a what? Is a vector quantity. Now, because the work done alone is acting as a force moving in direction, so it is a vector quantity. Then magnetic induction. When we talk about magnet does not just act. Magnet has a direction with which it acts in the direction of force, either the north side or the south side. So magnetic induction is a vector quantity. Acceleration due to gravity, of course, displacement, rate of change of velocity with time. Velocity is involved, so is a what? Is a vector quantity. Now, power is actually a function of a rate of expansion of energy, or rate of doing work, or I say it's a function of work with time. The rate of doing work is work over time. So, but the work at what direction? There is no direction. So it's just doing work. There is no direction. So power has no direction. So it can be exacted at any point. So it's a scalar quantity, it's not a vector quantity. So power is a vector, is a scalar quantity. Sorry, x. Now the last one is electric field. Electric field is actually an area with which electric current or electric force can be felt. So the direction or the path with which electric force can be felt in the electric. So there's a direction. The direction is a part of the force. So it's a what? A vector quantity. So that's it. So you can take note of this. Now let's come to you see, indicate the unit at the front. Yes, we should indicate the unit at the front. First of all, what is the unit of work? Work is actually, we talked about units in our last video. We talked about units, we talked about direction. So work is actually force times distance over time. So let me give you a shortcut. Force times distance over what? Sorry, work is actually force times distance. And what is our force? Force is what? Mass times acceleration, then this d times d. So what's our mass? We can say kilogram, yes. Then acceleration is meter per second. Then multiply by that distance again. So we can say kilogram meter per second square. Yes. So otherwise, work can also be regards to as what? Joule. Yes. So that's a bit of work. Then what about power? Power is actually work over time. So if it's work, so we can say it's joule per second. Are you getting it? Or we can say it's also kilogram, which is this kilogram meter per seconds. Consider this seconds cube now. So kilogram meter per seconds cube. So that's the unit of power. And in other words, we can also say it is tagged as what? Watt. So work done, not one unit of work done in time per seconds is power. Yes. And the kilogram meter per second square is also power. Then the collective name for this unit is tagged or refers to as what? Watt. So that's the unit watt. Then gravitational field. Gravitational field can actually be defined as is a product of the what? Of now. Gravitational potential. So if it is gravitational potential, the unit is actually Newton meter per kilogram. Yes. Newton meter per, and Newton meter is also referred to as what? Joule. So we can say joule per kilogram. So that's the use of gravitational field. Joule per kilogram. So what about pressure? Pressure is actually force over area. So force over area is pressure. So the unit is what? Force is what? Newton. Newton over area. So we can say Newton area is what? Meter square, right? So it's Newton per meter square. Yeah. Specific heat capacity, I told you that is the work done, is the rate at which heat is heated on an object with a temperature rise of 1 degree Celsius. So heat is actually measured in joule. Then the object, the mass of an object, which is what? In kilogram. Then taking temperature into consideration, then degrees Celsius, so Kelvin. So joule per kilogram per Kelvin, or you can say per degree Celsius. Now density is what? Mass over what? Over volume. So mass is what? Kilogram, and volume is what? Is in meter, kilogram per meter cube. Yes. So that's the unit. Then elastic constant. This is deduced from Hooke's law. Hooke's law states that the force on an object taking into consideration the extension. Now we have F is equal to KE. That is the product of the force, the constant, and the extension. So now what's the constant there? The K now, which is the ratio of the force to the extension. So the elastic constant now, which is K, which is equal to F over E now. F over is equal to what? The force is in Newton, then the extension is in meter. So the unit of elastic constant is what? Newton per meter. What about electric field? Electric field is actually the ratio of the force to the charge. The ratio with which the force is moving the charge in an electric circuit or in the conductor is electric field. So we can say the unit of electric field is what? Newton per coulomb. Yes. Now potential difference. Potential difference is the work done when a coulomb of charge moves from one point to another in an electric circuit. So work done. From there you can say work done V is equal to work done, which is W over Q. So what is W? W is J, joule, then coulomb. So we can say joule per coulomb. So that's the unit of potential difference. Then resistivity. Yeah. Ohms per meter. Yeah. So that's it. It's actually very straightforward. So just get acquainted with your units in physics. Know the difference between scalar quantity and vector quantity. This scalar vector is very important. So try to understand them appropriately, and I'm telling you, with something like this, you do exploit. Thank you very much. Yes. Please place your comments on anywhere you're having challenges. I will see you in the next video. Love you.